In recent years, the development of humanoid robots has reached a qualitatively new level, and one of the most discussed projects in this field has become Tesla Optimus, developed by Tesla under the leadership of Elon Musk. If in the early stages Optimus was perceived as an experimental platform for labor automation, recently there have been signs that Tesla is considering a much more ambitious goal: the creation of an architecture that functionally approaches the principles of how the human brain works. From a scientific point of view, it is important to clarify immediately: this is not about literally reproducing the biological brain. The human brain is an extremely complex system containing about 86 billion neurons interacting through trillions of synapses. It has been formed over millions of years of evolution and possesses not only computational, but also biochemical, energetic, and adaptive features that cannot be fully reproduced in an artificial system. However, modern science and engineering are increasingly turning to the idea of creating a functional analog, that is, a system that does not copy the structure of the brain, but reproduces the key principles of its operation. One of such directions is neuromorphic architecture, a field at the intersection of computer science, neurobiology, and engineering. Unlike traditional computing systems, where information processing occurs sequentially or within strictly defined structures, neuromorphic systems aim to imitate the distributed, parallel, and associative data processing characteristic of the brain. This means that information in such a system does not simply pass through an algorithm, but spreads across a network where different nodes can change their activity depending on context, previous experience, and current tasks. If such principles are implemented in Optimus, this will lead to a fundamental change in its behavior. Modern robots, even those equipped with advanced neural networks, mostly operate according to the input processing output scheme. Cameras and sensors collect data. Algorithms recognize objects and situations, after which the system makes a decision and performs an action. This approach is effective but limited. It does not imply deep interpretation of what is happening and does not form a stable understanding of the environment. In the case of implementing a neuromorphic or hybrid cognitive architecture, the robot gains the ability to operate differently. A layer appears that is responsible for integrating information from different sources: visual, auditory, and tactile. Then a context is formed, which may include not only the current situation, but also accumulated experience. This allows the system to make decisions not simply based on current data, but taking into account similar situations in the past. A particularly important element is memory. In classical systems, memory is represented as a database or a set of model parameters. In more complex cognitive architectures, it becomes dynamic. Events are linked to each other, associations are formed, and priorities emerge. This brings the system closer to what in cognitive science is called episodic and semantic memory. As a result, the robot can not only know, but also remember, albeit in a technical sense. Special attention should be paid to the issue of emotion imitation. From a scientific point of view, emotions in the human brain are the result of complex interactions between neural networks, the hormonal system, and evolutionary mechanisms. In artificial systems, this can only involve modeling behavioral responses that outwardly resemble emotional ones. Nevertheless, even such imitation can significantly increase the effectiveness of human-machine interaction. A robot capable of adapting tone, reaction speed, and behavior, depending on the user's state, is perceived as more understandable and natural. Technologically, such a system will most likely represent a hybrid of local computing and cloud infrastructure. The local module provides fast response and basic autonomy, while cloud systems provide access to more complex models and continuously updated data. This approach is already used in a number of modern AI systems and makes it possible to combine speed and scalability. If we consider the practical implications, the implementation of such an architecture could significantly expand the scope of application of humanoid robots. In industry, this would make it possible to move away from narrowly specialized automated lines toward universal systems capable of adapting to various tasks. In the service sector and everyday life, robots capable of interacting with people at a higher level will appear, taking into account individual characteristics and preferences. In medicine, such systems can be used to monitor patient conditions and assist medical personnel. However, along with technological possibilities, new questions arise. If a system demonstrates behavior similar to human behavior, the problem of interpreting that behavior emerges. Users may attribute qualities to the machine that it does not actually possess. This requires the development of new approaches to interface design, as well as ethical and legal standards. Thus, a possible update of the Tesla Optimus architecture toward a functional analog of the brain represents not just an improvement of individual characteristics, but an attempt to change the very principle of how the robot operates. This is a transition from an instrumental model to a cognitive system capable of adaptation, learning, and more complex interaction with the environment. Despite the fact that full implementation of such ideas is still far away, the direction in which the industry is moving already points to deep changes in the understanding of what artificial intelligence is and what role it will play in the future. And here it is important to add one more fundamentally significant aspect that is often overlooked in discussions of such technologies: real-time learning. Traditional neural networks, even the most advanced ones, are trained on pre-prepared datasets, after which their behavior is fixed and only periodically updated. However, an architecture closer to the principles of how the brain works implies continuous adaptation. This means that Tesla Optimus could potentially change its behavior models directly during interaction with the environment, and not only after updates from Tesla developers. From a scientific point of view, this can be compared to mechanisms of neuroplasticity, the brain's ability to change its neural connections in response to experience. In artificial systems, this is implemented through dynamic adjustment of weights and structures within the model, as well as through the addition of new connections between system nodes. As a result, the robot does not simply perform tasks, but gradually forms its own model of the world, which becomes increasingly accurate and personalized. Another important element is predictive mechanisms. The human brain constantly builds forecasts about what will happen next and adjusts behavior based on discrepancies between expectation and reality. If a similar principle is implemented in Optimus, it will allow it to act proactively. For example, it will not just respond to commands but anticipate human actions, optimizing its responses and reducing reaction time. This is especially important in dynamic environments, where even fractions of a second of delay can be critical. In addition, such an architecture opens the way to more complex forms of coordination between multiple robots. If each of them has a system capable of interpreting context and exchanging information at a higher level, the possibility of collective behavior emerges, resembling social systems. This could lead to the creation of distributed networks of robots that function as a single organism, sharing experience and synchronizing actions. Thus, we are not talking about simply adding a smart module to an existing robot, but about a transition to a fundamentally different paradigm. In this paradigm, the robot becomes not a set of algorithms, but an adaptive system capable of learning, prediction, and complex interaction. And if Elon Musk actually implements even part of these ideas in practice, it could become one of the most significant technological shifts in the history of robotics and artificial intelligence.